In this example, we're given a circuit that is driven by a sinusoidal current source in here, and this is basically the sinusoidal current source, and it has an omega. Let me just write this here. So the omega for it is just simply 200,000 radian per second, okay? That's the unit for that, okay? And what we're being asked to compute is the voltage across all these shared elements in here, the current in the first branch, second branch, and the third branch. There's multiple ways we can solve this. The way I'm going to do it right now is using current division and just basic circuit analysis technique. No nodal, no nothing else. So the first thing we need to do is actually, I'm going to take this here and I'll just copy it just in case we need it. And I'll convert it to the phasor domain. So how do we convert it to the phasor domain? Well, here's what we do. So the first thing I will do is, let me just do that here. There you go. So we'll do this here as an image, okay, and we'll convert it to the phasor domain. All right, so how do I convert this current source? Well, the current source is A times this here, okay, so what's the phase angle for that? The phase is 0 for this here. I'm looking at that. The phase is 0. The frequency is 200,000. So let me just make sure here. I'll write the frequency so that we don't forget it. The omega is just 200,000. And okay, so how do we convert this? Well, this is simply 8 and the angle is 0 because the magnitude happened to be 8. Okay, and it's in cosine. So what about the 10 in here? Well, the 10 is still 10. Nothing changes in here. So this is what can be. The 6 stays 6. And what about this one here? Well, this one here is just simply j omega L. Okay, so let me just compute with the j omega. Well, omega is 200,000. Okay, and well, let me just write it in here. So write it, j omega L is just simply j times 200,000 and times L, which is 40 times 10 to the negative 6. And that gave me exactly 8. So we can do this here, and I can replace it with its value, okay? I can replace it with, I'll replace this one here, and I can tell you that here is just simply 8J, okay? Ohms, of course. What about the capacitor? For the capacitor, actually, here's what we have. It's 1 divided by j omega c, which is 1 divided by j, 200,000, 1, 2, 3, and the c is 1 times 10 to the negative 6. So the answer is 1 divided by j of 5. Actually, it is not. It's just simply 5 times 1 divided by j, or 5 divided by j, or negative 5j. Okay, so I'll replace it with its value in here. So this one here becomes the following. So this one here, it becomes, well, I didn't have to remove the capacitor, but I can't, it doesn't matter, 5j. Well, actually, let me just do it that way, the proper way. Okay, here, and then that, and then this is what we get, negative 5j ohms. Okay, so that's what we have. Okay, so now we converted this particular circuit to the phasor domain. Of course, that leaves me the following. So this current in here, instead of being I1, it becomes uppercase I1. So this is uppercase I1. This is uppercase I2. It's not a function of time anymore. This is uppercase I3. This is not a function of time. This is just V. And of course, this one here is just simply I of S. Okay, so now we have everything to do. We're in the phasor domain, so we have everything we need. What we're being asked to compute is what I1, I2, I3, and V. Actually, we're asked to compute it in the time domain, but it's easy to convert once we get the phasor representation of phasor domain current. So the first thing I'm going to do, since we're not using any fancy analysis technique, is I'll combine these to find what the Z equivalent is. So they're in parallel. Of course, I have this one here, and this one here. So the Z equivalent seen by the source is the following. So 1 over Z equivalent is simply 1 over 10 plus 1 over, hopefully you agree, this is 6 plus 8j. I can combine these two together, 6 plus 8j, okay, plus, I believe we can say 1 divided by negative 5j. All right, so now we can figure out what Z equivalent is. And what I got on my calculator is I got the 1 over Z equivalent. This here result, this is 1 over Z equivalent, okay? And this is 0.16 plus 0.12 J, okay? What we need for the Z equivalent is the reciprocal of that. And what I ended up with is 4 minus 3j ohms. This is the Z equivalent for all of them. Okay, so why am I computing the Z equivalent? Because frankly speaking, I can now figure out what the V is. Okay, so the voltage simply is based on Ohm's law. It's just I times R, right? Or I times Z for that matter. Okay, so it's I times Z equivalent. But what is I? Well, I is just simply 8 in the 0 degree, and the Z equivalent is 4 minus 3J. Of course, they're in different formats, but we can use a calculator to compute what that is. And that is here, I'll just multiply it by 8, okay? And what we get is the following. We get 32 minus 24J. And that's basically in volts. Okay, of course we can convert it to any other formats we want. So for example, if we want it in the phasor domain representation, that's what we get in here. What we get, not phasor domain, exponential, it becomes 40. That's the magnitude, and this one here is negative 36 point, let's say 87 degrees volts. All right, so now what else do we need? Well, if we needed the I1 and I2 and I3, we can just use Ohm's law. Okay, but before I continue, well, what we have now is V in the phasor domain. What if I wanted it in the time domain? Well, the transformation or the inverse phasor transform is simple. V of t is just simply, well, what's the magnitude? It's 40. Cosine, what is the omega? Well, the omega, we kept it in here because we need it, is 200, okay, 1,000, 200,000 t, and negative 36.87 degrees. And that's volt. So this is basically the voltage going across this in the time domain. Basically, I computed this V of t here. So to sum, what we've done is I moved to the phasor domain. I figured out what the Z equivalent. I use the Z equivalent with Ohm's law in the phasor domain. I figured out what the V in the phasor, and then I transferred it back, and that's what I got. Now, if I needed any of the other currents, for example, I1, I2, or I3, whatever it is that we want, we can either just divide. For example, if I want I1, well, I know what the V is. All I have to do is just use Ohm's law. You can use Ohm's law, or I can use current division. So I'll use current division just to show you that it applies as well. And I'll use current division, for example, to figure out what I2 is, okay? So let's figure out what I2 is. Well, according to current division, I2 is the I source, okay, times the Z equivalent, I believe, divided by the Z2 that I'm interested in. This is basically the general rule for current division. Okay, so let's do that here. What is the I of S? This is 8, 0 degrees. The Z equivalent is 4 minus 3J. What is Z2? Z2 is actually this here, which is 6 plus 8J. Okay, so this one here is 6 plus 8J. Okay, so let me compute this for you. And I ended up with just simply negative 4J. That's what I ended up with. J. Okay, and that's here is amp in the phasor domain. Of course, if I'm to convert it to exponential format, for example, in here, what I'll end up with is 4, and this one here is negative 90 degrees amps. Okay, so I can figure out I2T is by simply saying it's 4 times cosine 200,000 T. Okay, negative 90 degrees. Okay, and that's basically an amp. All right, so that's what that is. Well, let's double check our answer. Our answer should be, well, I have to simply using Ohm's law should be V, the one that we computed in here, divided by Z of 2. Okay, so what is V? Well, the V that we got is the following. We got here, where is V? V happened to be 32 minus 24J divided by Z2. Well, Z2 is this here, which is 6 plus 8J. Okay, so let's divide this here. It becomes 6 plus 8J. Okay, and we get the following. Frankly speaking, I can see it because this 8 times 4 is 32, and 8 times 3 is actually 24. So it is the same answer. We'll get the same exact answer. And you can figure out the rest of the currents in the same way. You can apply current division to figure out what this I3 is, what this I1 is, and it's pretty straightforward.